Simon Godskesen's presentation. Is bachelor's thesis in mathematics. And I'm a supervisor, Raza Sainuddin. I'm in the math department, and Simon will be talking about simulating transmission processes on networks.
Just go ahead then.
Yeah.
Okay, yes. Greetings. Well, he introduced me. I'm Simon Godskesen. I'm going to write written about simulating transmission processes on networks. So, understanding the dynamics of how an infection spreads in a population and how the underlying contact network affects its behavior is crucial to preventing future outbreaks of COVID-19 and other contagions. In this case, a contact network is a mathematical graph which consists of nodes and connection between the nodes, which allows them to communicate and exchange information. So modeling transmission is often done in some analytical way using a series of differential equations. But since a virus is inherently probabilistic, then we choose a stochastic model where the time between infections and recoveries is exponentially distributed with some rate. So the purpose of this project is to explore the different types of transmission models, build a simulator to simulate transmission processes on networks using different transmission models, and study how the network topology affects the transmission process. So the outline is going to be like this. In the first part, I'm going to talk about transmission models, which states are available for each node. Then the second part is about the transmission tree, binary tree that describes the path of the contagion as it infects new nodes. It keeps track of the infector and the infectee pair, as in who infected whom. Then I'm going to say a few words about the structure of three specific deterministic networks, the three primary networks that are important for the simulations, and we should also see why they're important in this section. A quick overview of the code skeleton for the simulator, how is the code structured, and then finally the purpose of the simulator and their result. What are we simulating and why? So the transmission model dictates which states are available for each node. The simplest model is the SI model, and it's a susceptible infected. And susceptible nodes are infected at a rate lambda 1 per infected neighbor, and infected neighbor stays infected forever. There's only one final outcome for this model, and that every single node is infected, and that's the only way that a simulation can end. So since it is at a rate lambda 1 per infected neighbor, then more neighbors is going to increase the chance of becoming infected. You're going to become infected quicker. This model is not very good for describing diseases because it doesn't have the recovered state, and most diseases you're not infected forever. But it can be used to describe transmission of something else, such as information, where an infected node is it's a person that have seen some news, and susceptible nodes are people who haven't seen the news, and then those connections could be seen as some social media post or people just talking in general. Then we have the SIR model, susceptible, infected, recovered. Infected nodes recover at a rate lambda 2. Recovered nodes stayed recovered forever, and recovered nodes can block the path between infected and susceptible nodes. And so if there are some node that has many neighbors, and this node recovers, then it can effectively block the infection from those susceptible nodes. Now, this model can be used to describe things that you can only be infected by once, such as chickenpox. The recovery is you have developed an immunity through either vaccines or your own immune system. For this model, there's two events that can happen at every step, and that is either an infection event or a recovery event. And we shall see later how these events are selected later. Now, there are many possible outcomes for an SIR model, since you could potentially the virus doesn't have to affect every single node. Like there's a possibility that that every infected node can recover, and then leaving some of the nodes still susceptible, and the virus is gone. And then lastly, we have the SIS model, where it's susceptible, infected, susceptible. Infected nodes turn susceptible at a rate lambda 2. We call this still a recovery event, even though they're not recovered state, they just go back to susceptible. And the states looping back to susceptible cause some interesting dynamics to emerge, such as the contagion never dying out. It depends, of course, on the parameters lambda 1 and lambda 2. So for the SI model, we denote node I, Ni, and the state of node I is Si, which is 0 if it is susceptible, and 1 if it is infected. Then we define this set S, which consists of the state of every single node in the system, and S of Z to be the state of the system at event Z. Then we have the tau of Z, which is tau of Z is a transmission tree. We're gonna talk a bit more about it later, but right now it is enough to know that it is a transmission tree that describes the path of the contagion and keeping track of the infector and infectee, and where did the infection come from and who did they infect. And so we define this variable x, which is the tree and the state, to be it's a double that fully describe the system at event Z. And this is one of the most important statistics that we're going to be looking at. So we let I be the set of possible outcomes after a single infection event happen to X, and let N of C be the total number of infectious connections. In this case, an infection, it is not the number of susceptible nodes, it is the number of connections between an infected node and a susceptible one. And so if you have just one node that is infected and it's connected to 4 susceptible nodes, and N of C is 4. But in theory, we could have had, millions of susceptible nodes that are not connected to this infected node. And so it's important to know that this is the number of infectious connections. And then we have the transition probability, and this should be read as such, like we're in the state C, and we're transitioning into state M. Can you see my cursor still, by the way? Can anyone see my cursor?
No.
I cannot see it.
Okay, well then I have to just describe it better. Okay.
Now saw something moving though.
Oh well.
Maybe when you move it, it's visible. I don't know.
No, I'm moving it all the time. Anyway, if we're in the state C right now and we're gonna transition into M, then if M is an infection event, it belongs to this set of I, then the probability of that happening is just 1 over the number of connections. Because every connection has an equal probability of happening. And if M is not a state that can happen, then the probability is 0. We can see this as a Markov chain with a generated Q, and we say that we're in state X of Z and we're transitioning into M. Then the Markov generator is just lambda 1 if M is an infection event. However, if M is the same event that we're still in, then it is negative lambda 1 times the number of connections. And so, well, it's a generator, so we can see this kind of like time spent in the current state. So if lambda 1 increases or the number of connections increases, then this negative number will become, well, more negative or larger, I guess. And so the time spent in the current state will decrease, and the time taken to we will quicker transition into a new state. So an outbreak is guaranteed with the SI model, which is why we also have the SIR model that introduces a new state, which is recovered. Recovered nodes stay recovered forever, and infected nodes recovered at a rate lambda 2. So now we have two events that can happening, and so the time between any event is exponentially distributed with some rate lambda, and that is the number of connections times lambda 1 plus the number of infected nodes times lambda 2. That is just how many of these events that can take place. And so by the law of competing exponentials, then we can calculate what is the probability of having a certain event. So the probability of having an infection event is just the number of connections times lambda 1 divided by this total lambda. And conversely, the probability of having a recovery event is just 1 minus the delta Z. And so it's just a number of infected nodes times lambda 2 divided by the entire lambda. So now we have two events taking place. And so how does this affect the transition probabilities? Well, similarly to I, we define R to be the set of all possible outcomes after a single recovery event happened to X. And now the transition probability depends on what M is. Again, we're in the state C, and we're going to transition into state M. Then if M is an infection event, then it's the probability of having an infection event divided by the number of connections, which is lambda 1 over lambda. If M is instead a recovery event, then it is 1, where it's the probability of having a recovery event then divided by the number of infected nodes, which is lambda 2 over lambda, and it's 0 otherwise. And likewise, with the Markov chain generator, it is lambda 1 if it's an infection event, it's lambda 2 if it's a recovery event, and it's negative lambda if it is the same, if we're transitioning into the same state. And so this, well, maybe it should be made clear if this lambda was written out the entire expression, but it goes up with lambda 1, lambda 2, and the number of connections and infected nodes. And so the more infected nodes you have and the more connections there are, the less time we spend in the state that we're in. So the biggest difference between SI and SIR model is the possibility of not having an outbreak. Theoretically, every single infected node could recover, and then leaving some of the nodes still susceptible, even though the virus is gone. And we say for example, that we have 5 infected nodes. And if we get 5 recovery events in a row, then the virus is gone, and we could have still millions of susceptible nodes. And so one of the interesting statistics of the SIR model is the probability of the simulation ending with a certain amount of recovered nodes. And in this case, the recovered nodes, having a recovered node at the end of the simulation means that this node has been affected by the virus at some point. And then where we can look at, and when the simulation ends, we just look at how many recovered nodes we have as opposed to susceptible. And so we can calculate the probability of having a certain amount of recovered nodes, and in particular the probability of the initially infected node recovering before infecting any other node is just lambda 2 over the number of connections times lambda 1 plus lambda 2. You can calculate it for more. In the report, I also do it for 2, but getting for 3 and 4 and all the way up to 100, it's going to be impossible because of how intertwined the events can be. Like you can have, like say you want to have calculate 5 recovered nodes, then you have to calculate, okay, well, you can have 2 infection events, and then a recovery event, and then 2 more infection events, and then 4 recovery events, and back and forth. And you have to calculate every possibility, and that is, well, that's a new thesis in itself, so I didn't do that. So the probability of just recovering all at once, it depends on this number of connections, which depends on the network itself. And we shall see a little bit later how that changes. Then lastly, we have the SIS model. It doesn't change quite a lot from the SIR in terms of the transition probabilities. But now we skip the state recovered and we just go back to susceptible again. And infected nodes turn susceptible at a rate lambda 2. And similar to I and R, we now define S to be the set of all possible outcomes after a single recovery event happened to X. And now, as said before, a recovery event in this context is a infected node turning susceptible. Then the transition probability is, well, we're in the state C again, we're transitioning into M. Then it's the same as if infection event, probability of having an infection event divided by the number of connections, if it is an infection event. And then if it's a recovery event, then the probability of having a recovery event divided by the number of infected nodes. And the Markov chain generator is unchanged from before. And that concludes the transmission models, and we move on to the transmission tree. So the transmission tree is a rooted, ranked, planar, leaf-labeled binary tree. It is rooted because, well, it has a root, and is ranked because the internal labels increases as you go down in the tree. It's planar because it's two-dimensional. It's leaf-labeled means that, well, all the leaves are labeled by their respective node label, and it's binary because every node only have 2 children. It describes the path of the contagion as it moves through the network, and the internal vertices describe the infection event number, and the leaf labels describe the node themselves. So for every infection, the infector goes to the left and the infectee goes to the right. So it could be a little tricky to read this transmission tree, but it should be read like this. Say, for example, we want to find the second. Okay, now it's actually really good if you could see my cursor. Let me just share it again like this. Can you see my cursor now?
Yes.
Do you see it now?
I can at least.
Okay, great. So let's see, did I move too quick? Yes, I did. Okay, so we have the second event right here, and we want to find who infected and who got infected as the second event. Then we look at, this is the left subtree, and then this is the right subtree of internal vertex labeled 2. And to find the infector, we just go all the way to the left of the left subtree and we find N0. And then we go all the way to the left of the right subtree and we find N2. And so the second event was from N0 to N2. And same with, say we want to find infection 6, then all the way to the left of the left subtree, which is N2, and then all the way left of the right subtree, which is N7. And so the infection was from N2 to N7. There are 3 deterministic networks that we're going to talk about in the simulations, and we're going to see a bit how they look like. The first one here is the star network, which has a star node in the middle that is connected to every outer node, and every outer node is only connected to the star node. For the path node, then every node is connected to 2 of its closest adjacent neighbors, except for the first and last, which are only connected to 1 neighbor. And then last, we have the complete network, which is every node is connected to every other node, and so this one is completely symmetrical. So for every simulation, it is the 0th node that is the initially infected node. And this is because Well, for the star network, say we were infecting node number 5 at first. Well, the first thing that's going to happen is an infection spreading to the star node, and then from there, it just transmission on a star network, but with one fewer outer nodes, since that's where we started. And so there's no point in starting anywhere else because it's going to look the same. And for the path network, say we want to begin at path node number 2, then starting at node number 2, well, that's technically just having two transmissions on two different path nodes because they go in different directions. And so it doesn't really give us any new information either. So the complete network, well, it's a completely symmetrical, so it doesn't matter where we begin. So we just say that we begin at 0 node. So why are these networks interesting? Why do we care? Well, we care because the tree shape is unique. So for the SIR model, that when the state doesn't loop, it's just SIR, then the star network, well, it's only the star node that can infect other nodes because the other nodes are not connected to each other. And so every infection is going to cause the transmission tree to be shaped towards the left. Whereas for the path network, only the latest infectee can become the next infector. And so the tree will be shaped all the way to the right. And for the complete network, well, since it's a complete unbiased network toward any node, then, well, we can have any shape with equal probability. And any other network can be seen as a sort of mix of these three styles in some way. So the code skeleton, this is how the simulation is made. So we generate the transition probability. This is the probability of having an infection event. And then we generate a random variable p, which is uniform from 0 to 1. And then if p is lower than this infection, this delta, then we have an infection event. And so we choose the random infectious connection uniformly and mark the susceptible node infected. Otherwise, then is a recovery event, and we mark the random infected node. Well, we choose the random infected node uniformly, and we mark it either recovered or susceptible, depending on the model. And then we do this until there are no more infected nodes or a maximum number of events have occurred. So for the SIS model, we can't really expect that the infection go away at some point. So we have a maximum amount of events that is arbitrarily chosen before. Okay, so what are we simulating and why? Well, we're putting lambda 1 is equal to 1, and we're having 30 nodes. The reason lambda 1 is equal to 1 is because, well, the actual values of lambda 1 and lambda 2 doesn't really matter. It's just the ratio that matters. And so we could just put lambda 1 to 1, and then we can change lambda 2 to get some behavior that we want. And so for the SIR model, then we're going to simulate 1,000 transmissions on every network for 4 different values of lambda 2. And for each lambda 2 network, we're going to study how many of the nodes are recovered when the simulation ends. And then we'll look at the frequency of k nodes being recovered, where k is a number between 1 and 30, because we can't have more than 30 recovered nodes because we only have 30 nodes. So for the SIS model, then we simulate a 15,000 event transmission for each network. 15,000 is just, well, it's somewhat arbitrary, but whenever I did more than 15,000, then the program crashed. So I don't know why. So we look at the distribution of the infector and infectee frequency for every node. We do a simulation, also do a simulation on a small world network, which is a fourth network I haven't shown you yet. We're gonna see why. And we study the relationship between the number of neighbors and the infector and infectee frequency. So this is a graph. It shows the frequency of simulations ending with X recovered nodes. For 4 different values of lambda 2. The red plot shows when lambda 2 is 1/2. The frequency is quite low for recovered for few recovered nodes, but it's still everyone is still greater than 0. And increasing the frequency with increasing as x increases, then we get a more and more frequency, more and more counts of so many recovered nodes. It is very likely to infect every single node, like 28, 29, and 30, almost the majority of the simulations. So the blue is lambda 2 is equal to 1, and now lambda 1 and 2 are equal, and you see that the frequency is almost completely uniform. There's a little bump here in the middle, but I'm pretty sure it should be uniform. Green is when lambda 2 is 5, and we see that we have a much higher chance of fewer recovered nodes, and there are now no counts of more than 28 recovered nodes, and so none of the simulations affected every single node. Yellow is lambda 2 is equal to 10, and we have a significantly higher chance of having very few recovered nodes. The frequency is drastically reduced very quickly, and there are actually no counts of more than 21 recovered nodes for this star network. So on the path network, it looks somewhat similar. When lambda 2 is 1/16, then we have a big bump at the 30 recovered nodes, which means that, well, it is the most common ending with for simulations for SIR on path network. It is unlikely to have recovery events before everyone is infected. When lambda 2 is 1/8, then behavior is similar behavior, but with a smaller bump at 30 nodes. And now we just double the probability of having a recovery event, and so fewer are going to survive this. Well, sorry, more are going to survive this. And since the path network, if the latest infectee recovers, then the entire infection is contained within the subset of the nodes, that the infection cannot jump over the recovered node since it just stops. And so when lambda 2 is 1/3, then we have much greater frequency of fewer nodes, and there are no counts of more than 22 recovered nodes. When lambda 1 is 1, then almost half of all simulation ended immediately before infecting any other node. It quickly drops after that, and it's very unlikely to have more than 5 recovered nodes. There are no counts of more than 11 recovered nodes. So SIR complete, it is much more polarized. Like we either have either it dies out immediately or everyone is infected. Well, there's some here in the middle, but much more polarized than before. So the number of, in this case, the number of infected nodes is always overwhelmed by the large number of infectious connections, and so we're going to have a snowball effect. So if you look at for the frequency of having one recovered node, then you can see how it's monotonely increasing as we increases lambda 2. And so as lambda 2 is increases, then we're getting more and more counts of 0, well, 1 recovered node. There's a large bump here for red, lambda 2 is equal to 5. And we can see that every color has their own little bump, and it seems like this bump is moving to the left as you're increasing lambda 2. You see that the bump is at 30 for red, 29 for blue, and then 27, 28 for green, and then 25 for yellow, and then it keeps going down as you're increasing lambda 2. Hard to see the purple, but should be somewhere around 20, I guess. So this is the SIS model on a star network. So the plot shows the infector and infectee frequency for all nodes except the star node. The x axis is the node label. So what does it mean? It means that, for example, if node number 5 here, you can see that the infector frequency for node 5 was, well, around 3. And so it infected 3 nodes, whereas the infectee frequency for node label 5 was around 75, around here. And so this node was infected 75 times, but it only infected some other node 5 or 3, 4 times. So the star node is excluded because of its large infector frequency. It was 2,394 as opposed to the everyone else's infector frequency, which was, around 5. And so it's going to be super huge, and even at logarithmic scale, it was going to be very difficult to see what was going on. Its infector frequency was 118. And so you might wonder why the star node infector frequency was so much higher than the infectee frequency. And this comes from, well, the star node have more connections than any other, so it's going to infect more. But in order for the star node to be an infectee, it has to loop back to susceptible and then become infected again. And when we have a recovery event and an infected node is turning susceptible, then we're choosing a infected node uniformly. We're not checking how many neighbors they have, how many connections they have. And so it has to go through this uniform selection of infected nodes. And so as soon as the star node is the difference is that the star node is susceptible. The only thing that can happen is an outer node infecting the star node, and as soon as the star node is susceptible, it's going to get infected again. But when it got infected, then it has to go through the uniform selection that every node is going through, and so it's going not to have very high infectee frequency. As for the path network, it's mostly uniform, except at the edges for node 0 and 29. And they have significantly smaller frequency. And that is because they only have one connection. And so everyone else have 2 and this is 1. Why isn't it really, why isn't it just half of what the other are? Well, that is because they have they have lower chance of becoming infected and infecting others, but there's a double effect. It should actually be 4 times fewer frequency because let's see. Well, when they are susceptible, then there's only one that can infect them, and as soon as they got infected, then the probability of them recovering is the same as for everyone else, and so they're going to be staying infected longer, and they're also going to be staying susceptible for longer, and so they don't really have anything to infect, and so the frequency is going to be much lower for them than for anyone else. And then lastly, we have the SIS model on complete network, which is, you have to look at the scales. It's from 230 to 270, and it looks, right here, it looks like spiky, but it's actually quite uniform. Should have changed the scale here. It's really easier to see, but there's no bias towards any node. Every node has just completely symmetrical to any other node, and so it behaves about what is expected of it. And then lastly, we have the SIS model on small world network. The small world network is created by, you create a ring of n nodes, and then every node is connected to k of its closest adjacent nodes. And then for each existing connection, we add another connection to a random node with probability p. And so, well, we're studying this because we want to have a relationship between the infector infectee frequency and the number of neighbors and see how they relate to each other. And well, for this network, we don't have any information about the network before we construct it. And so we're going to be looking at a different statistic than before. And the reason why I chose a small world, where it's arbitrary. I just wanted a network that have a large variation in the number of neighbors. But the code works for any network at all. So the left picture shows the infector frequency as a function of number of neighbors, and the right picture shows the infectee frequency. And each blue dot is a node, and both of them we see a clear upwards trend, implying both that the infector and infectee frequency positively correlated to the number of neighbors as we expect. The infectee frequency, however, is a bit more constant. I think this guy at the top right is a bit of an outlier. But there's one thing to think about when the infectee frequency is, in order to increase your infectee frequency, then you need to go back to susceptible and then become infected again. And the uniform selection of infected nodes in the case of a recovery event is independent of how many neighbors you have. So even though the you become infected faster if you have more neighbors, you don't become susceptible faster if you have more neighbors. And so this one is going to be a bit more flat than the infector frequency, but it's not really super clear here. I mean, it's not very, the slope is not very, what's it called? It's much lower slope than for the infector frequency. And well, as I said before, the similarity is general. It works for any directional network, not just the networks in this presentation. And so what we have done is mathematically formulated transmission models on networks. We have coded a simulator to simulate transmission arbitrary contact networks using any epidemic model. The code for all of this is in my GitHub that I can send. And we have seen how some network topologies affect the transmission process. So any questions?
Thanks for the talk, Simon. If you have any questions, please ask Simon directly now.
Yes. No questions?
Okay, I actually have a question for Simon.
Yes.
At one point in your simulator, I guess I thought you were sort of trying to attack this much more general problem where the contact network itself co-evolves with the epidemic, right? So that at least the simulation itself can allow us to give insights into certain behavioral changes that the nodes are taking, taking action. Say they're quarantining, following recommendations and things like this. So those things are actually still part of your simulation machinery, right? One could actually see the effect of, say, quarantine behavior followed to various extents and see how that affects a contact network during the course of, say, the SIS or SIR model.
You mean like when people get infected, they go into quarantine, or what do you mean?
Yeah, that's right. So if you have a quarantine regime recommended, say, by the state of Sweden or whatever, and then one could potentially emulate that in the simulations. Am I right?
Well, I have, let's see if I can share a different screen here. Shared screen. And then we go into transmission process. Here you can see my simulator here. So I have coded such that when a person gets sick, then it is a certain probability that they will block a certain path. And well, you can have so this is actually for an SIRS. I didn't talk about that, but I decided to show you with the probability of blocking. So now let's see, it has 90% chance. It's a complete network, and so it has every node is connected to every node. But now it's when a node gets sick, then every path has a 90% chance of being blocked, which means that a person goes into quarantine, goes into self-quarantine when they get sick and block most of their paths. And you can see how much this is for SIRS. And you can see how this behavior changes as well. If I were to remove it, then everyone is going to be infected at all time, and we're not going to have any susceptible nodes.
No, I think that's good. Yeah, thank you. So I think the actual, although you haven't written down the mathematical formalism for the generators, but I believe the simulator actually is formalizing what is normally called the Markov control process on the arbitrary contact network with quarantine behavioral regimes. That's good. Thanks.
So one cool thing I can show you is that what happens when the probability of blocking a certain node is correlated to how many in the population is sick. And so if I have so now when 1/3 of the population is sick, then every path is blocked. And so you can see how much more it oscillates. I can even place it even faster. So now half of the population has to be sick, and then I should take it higher, 5. So now when 20% of the population is sick, then they will block every single node. And so you can see here how it oscillates around that point, how it oscillates up and down, because of how as soon as the we have 300 nodes, and so as soon as the infected nodes goes over like 80, then every single node is going to be blocked. Every single path is going to be blocked. And so the number of infections immediately goes down, but then it goes up again because we have people are starting to not quarantine themselves anymore, and so we get a new wave.
No, that's really good. And I guess the underlying combinatorial structures are implemented in Sage Math library, right? Using digraphs. So it's completely amenable to standard, computational mathematical operators, right? Okay, that's good. Yeah, thanks a lot, Simon. I don't have any more questions. There are 2 more minutes before we finish. Does anyone else have any questions?
I don't have any questions, but I want to say thank you for the presentation.